Hello everyone, welcome to this lecture series in linear algebra. Today we are going to talk about some theorems on eigenvectors and eigenvalues. So we have already discussed this topic that a non-zero vector will be an eigenvector if it satisfies the equation Ax is equal to lambda x, where lambda is the corresponding eigenvalue, where lambda is any scalar. Okay. So now we take some theorems here, and these results can be utilized to find eigenvalues and eigenvectors in certain cases. The first theorem is that the matrix A has a eigenvalue 0 if and only if A is singular. So this is an important result in the sense that if you know that a eigenvalue is 0 for a matrix, then matrix is definitely singular. Or if you know that the matrix is singular, then it means that it is going to have at least one eigenvalue as 0. Okay. So a proof of this, that the eigenvalues lambda satisfy the characteristic equation, okay, determinant of A minus lambda equal to 0. So if lambda is equal to 0 is an eigenvalue, so lambda 0 will satisfy this. Okay, so that means lambda 0 satisfies this equation, or simply when lambda is 0 it is determinant A equal to 0. Okay, so clearly the matrix A is singular because determinant is 0. Okay, so that proves the result. Okay, so if you have any singular matrix, it will have at least one eigenvalue as 0. Okay, or if you know that one of the eigenvalue is 0, then definitely the matrix is a singular matrix. The second result is that if x is an eigenvector of A, then x cannot correspond to more than one eigenvalue of A. Okay, so the proof again, let if possible you have a eigenvector of A corresponding to two eigenvalues. Okay, so let x be an eigenvector of A that correspond to two distinct eigenvalues, lambda 1 and lambda 2 of A. That means if lambda 1 is an eigenvalue corresponding to x, so it will satisfy equation Ax is equal to lambda 1 x, and lambda 2 is also eigenvalue with x, so Ax is equal to lambda 2 x is also satisfied. Okay, so Ax is equal to lambda 1 x, that means x is an eigenvector corresponding eigenvalue lambda 1, and Ax is equal to lambda 2 x means x is an eigenvector with a eigenvalue lambda 2. Now because left hand sides are same, so right hand sides must be equal, so lambda 1 x must be equal to lambda 2 x. Okay, and so I can take this to other side to write that lambda 1 minus lambda 2 times x equals to 0. Now it's a homogeneous system with x being eigenvector must be non-zero vector, so that means coefficient must be 0. Okay, so lambda 1 minus lambda 2 must be 0 implies lambda 1 must be equal to lambda 2 since x is a eigenvector which are non-zero vectors. So that proves our second result. If a matrix A is invertible and lambda is an eigenvalue of A, then 1 by lambda is an eigenvalue of A inverse. Okay, so again it is really interesting that if matrix A is invertible, okay, if it is invertible, that means determinant A is non-zero or A is not a singular matrix, so that means lambda equal to 0 is not an eigenvalue. Okay, so all the eigenvalues of this matrix are non-zero, and if you know the eigenvalues of A, then immediately you know the eigenvalues of A inverse matrix. Okay, so again the proof, let lambda be an eigenvalue of A with corresponding eigenvector x, so that the eigenpair satisfies this equation Ax is equal to lambda x, and since A is invertible, so A inverse exists and we can pre-multiply with A inverse on both sides of this. Okay, so since A is invertible, A inverse exists and we pre-multiplying with A inverse gives A inverse Ax is equal to A inverse times lambda x. Okay, and A inverse A, we know it is identity, so it becomes Ix or simply x vector equals to lambda is a scalar, so it goes outside the matrix and we can write it as lambda time A inverse x. Since matrix is invertible, so lambda has to be a non-zero eigenvalue, and so we can divide with lambda. Okay, so A inverse x can be written as 1 by lambda times x because lambda is non-zero. If lambda is 0, matrix is singular and non-invertible. Okay, so lambda non-zero must be true, and so it gives us the proof. Okay, a matrix applied on x gives 1 by lambda times x. Okay, so we get a eigenvector x with eigenvalue 1 by lambda for A inverse matrix. Okay, so 1 by lambda is an eigenvalue of A inverse matrix with the same eigenvector x. Okay, now the next theorem is that if lambda is an eigenvalue of A, then lambda power m is an eigenvalue of A power m, where m is a positive integer. Okay, so that means if you know the eigenvalues of A, then immediately you can write the eigenvalues of A square, A cube, A4 and so on, any integer power of A. Okay, proof is again, say lambda is an eigenvalue of A with eigenvector x, then again this will be satisfied that A times x is equal to lambda times x. So now if I pre-multiply with A on both sides, so I can calculate A square x. Okay, so A square of x will be A times lambda x, and lambda is scalar, goes outside, so lambda times Ax, and Ax is already known, lambda times x, so we get lambda square x. So clearly A square x equals lambda square x means lambda square is an eigenvalue of A square matrix. Again to this, if we pre-multiply with A, okay, so we'll get A cube x equals A times lambda square x. Lambda square is again a scalar, goes outside, and Ax we know is lambda x, so again we get lambda cube x. So clearly this equation tells us that lambda cube is an eigenvalue of matrix A cube. Okay, and so if we continue this process, so we can write in general that A power mx is equal to lambda power mx, where m is an integer, positive. Okay, so clearly lambda power m is a eigenvalue of matrix A power m. If lambda is an eigenvalue of non-singular matrix A, then determinant A by lambda is an eigenvalue of the matrix of adjoint A. Okay, so if matrix is non-singular, that means the eigenvalue is non-zero. Okay, so we can easily divide this. Okay, so again to prove this, let lambda x is an eigenpair, that means lambda is an eigenvalue of non-singular matrix A with eigenvector x, so that this is satisfied. Ax is equal to lambda x, and here lambda is non-zero because matrix is non-singular. Now we can pre-multiply this with respect to adjoint A matrix. Okay, so we get is adjoint A times Ax is equal to adjoint A times lambda x. Lambda is a scalar, it goes outside, so we get lambda times adjoint Ax. On the left hand side it is adjoint A times A. Okay, and we know that adjoint A times A is determinant A times I. Okay, so left hand side becomes determinant A on x equal to lambda goes outside, adjoint Ax, and because lambda is non-zero, we can divide with lambda to write that adjoint A matrix times x is determinant A by lambda times x. So again you see that matrix multiplied with a vector equals scalar multiplied with the same vector x. So x is the eigenvector with corresponding eigenvalue as determinant A by lambda for the matrix of adjoint A. Okay, so this is again a interesting result. The next result is that if lambda is an eigenvalue of a matrix A, then lambda plus C is the eigenvalue of the matrix A plus C times I. Okay, where C is any scalar. Okay, so proof of this, let lambda be an eigenvalue of matrix A with eigenvector x, then clearly Ax is equal to lambda x is satisfied. And if now we calculate the A plus Ci times x, okay, this matrix times x. Okay, so A plus Ci times x will be by linearity A times x plus Ci times x. Identity times x is x vector itself, and Ax we know is lambda x. Okay, so this left and right hand side becomes lambda x plus Cx, and so we can take x vector outside. Lambda plus C is scalar, so it becomes a scalar, and so clearly A plus Ci times x equals lambda plus C times x. Okay, so x becomes the eigenvector and lambda plus C becomes the eigenvalue for this matrix A plus Ci. Okay, so that proves our result, that if you know the eigenvalues of A matrix, then we know the eigenvalues of A plus Ci matrix for any C as lambda plus C. Okay. Okay, so next theorem is that the characteristic roots of Hermitian matrix are always real. Okay, Hermitian matrix, if you remember, we discussed in first lecture that the matrix which satisfies A conjugate transpose equal to A is a Hermitian matrix. Okay, so again let lambda be the eigenvalue of the Hermitian matrix A with eigenvector x, so that Ax is equal to lambda x is satisfied. Okay, and if we pre-multiply this with x power theta, where x power theta means its conjugate transpose. Okay, so the conjugate transpose we are shortly denoting by this symbol theta. Okay, so if we pre-multiply with this vector to the first this equation, Ax is equal to lambda x, so it becomes x conjugate transpose times Ax is equal to x conjugate transpose times lambda x, and lambda is scalar, it goes outside to write this. Okay, so this is one equation. Then if we take the conjugate transpose of this equation 1, okay, so if we take transpose conjugate on both sides of this equation, so it becomes the left hand side transpose conjugate equal to the right hand side transpose conjugate. Okay, and we know that if we have product of matrices A B and its transpose will be B transpose A transpose. Okay, so if we have a product of matrix here, then its transpose conjugate will be the conjugate transpose of last into conjugate transpose of previous into conjugate transpose of previous. So we'll get x theta, a theta, and x theta theta. Okay, this thing. Okay, so last conjugate transpose will become first, then the middle one, and then the first one. Okay, similarly here the last one, then the middle one, x theta theta, and then first one lambda power theta, but that's a scalar that goes outside, and for scalar transpose has no meaning, so it's just the conjugate. Okay, uh, now the x theta power theta must be x, because it is the transpose, so row goes to column, column comes back to rows, and it is also conjugate, so a plus ib becomes a minus ib and then comes back to a plus ib. Okay, so x theta theta is nothing but x vector, and it is Hermitian matrix, so a theta matrix must be equal to a. Okay, a conjugate transpose is a, so we can substitute that. Okay, so x theta, a theta is a, x theta theta is x, and similarly x theta theta is x here. Okay, so we apply these two, and so from 1 and 2 you can see that the left hand sides are same, so right hand sides must be equal. Okay, so the right hand side lambda x theta x must be equal to conjugate lambda x theta x. If I take this to other side, then lambda minus lambda conjugate times x theta x must be 0, and because x is an eigenvector, so x is a non-zero vector, so x theta x is also non-zero, and so that means this equation is true only when this coefficient is 0, or lambda must be equal to lambda bar. Okay, so lambda must be equal to conjugate, and if lambda is complex, say a plus ib, then this is a minus ib, so they must be equal only when b is 0, that means lambda has to be real. Okay, so the eigenvalue lambda of Hermitian matrix is real, because only if it is real then this will be satisfied. Okay, another theorem is that the characteristic roots of Skew-Hermitian matrix are pure imaginary or 0. Okay, so we know that Skew-Hermitian means a conjugate transpose is equal to minus of a. Okay, so the proof is very similar to Hermitian matrix. Okay, we start with the eigen pair lambda x for matrix A, so that Ax is equal to lambda x. The same steps we pre-multiply with x power theta to this. Okay, so that's our first equation, and then we take conjugate transpose on both side. Okay, so again theta powers on both side, and again we write it as x theta a theta x theta theta. Okay, so this equation. Now the change comes that because now the matrix is Skew-Hermitian, so a power theta is minus of a. Okay, x theta theta is x, so here that minus sign we can take to this side to write this as minus lambda bar. Okay, and again from 1 and 2 left hand sides are same, so right hand sides must be equal. Okay, so in this case what we get is lambda plus lambda bar times x theta x equal to 0. X is eigenvector, so this must be non-zero, so lambda plus lambda bar must be 0, or lambda is minus of lambda conjugate. Okay, and so this will hold. You see, if you put lambda as a plus ib, then this lambda conjugate will be a minus ib. So this equation, if you solve, you will find that a is 0. Okay, so that means lambda is iota b, or it is pure imaginary. Okay, that's pure imaginary, or it will be 0 if that b is 0. Okay, so it immediately tells us that the eigenvalue lambda of Skew-Hermitian matrix A is pure imaginary or 0. Okay, so this result now that the characteristic roots of a unitary matrix are of unit modulus. Okay, that means they have absolute value 1. Okay, so if you are given a unitary matrix, all the eigenvalues of them matrix are having a property that their modulus value is 1, its absolute value is 1. Okay, so again say lambda, let A be a unitary matrix, that means it satisfies this A times A conjugate transpose is same as A conjugate transpose A is equal to identity. Okay, and let us take lambda to be a characteristic root eigenvalue corresponding to the eigenvector x of A. So it will satisfy Ax is equal to lambda x. There is an error here, that matrix is not symmetric but unitary. Okay, so it read it as unitary here. Okay, so Ax is equal to lambda x, and so if I take the conjugate transpose on both side of this. Okay, so take this whole power theta on both side. Okay, so it is Ax power theta lambda x power theta. On this side we have product, so we will get x theta times A theta, and on this side we will get lambda conjugate times x theta. Okay, now if I calculate this product x theta a theta multiplied with ax, okay, then the right hand sides will also multiplied. Okay, so if I calculate the left hand side of 2 multiplied with the left hand side of 1, then it will be right hand side of 2 multiplied with right hand side of 1, and now it is easy to see that lambda conjugate times lambda is modulus of lambda square times x theta x, and on this side x theta ax, and a theta is identity, so it will become x theta x. Okay, so again this is identity, so x theta x equals to modulus lambda square x theta x. Take this to other side, so we'll get 1 minus mod lambda square x theta x. X is eigenvector, so non-zero, so x theta x is also non-zero, and so lambda modulus of lambda square must be equal to 1. Okay, or mod lambda must be 1. Okay, so it proves the result that the eigenvalues of unitary matrix, okay, they are of absolute value 1. Okay, now we take one very important result, which is known as the Cayley Hamilton theorem, and it says that every square matrix over real or complex field satisfies its own characteristic equation. Okay, so if you are given the nth order matrix A, okay, then we know the characteristic equation for that matrix is determinant of A minus lambda I is equal to 0. Okay, and it is because A is a matrix of numbers, identity is of same size. Okay, so only lambda is the variable here, and if you solve the determinant, it is a polynomial of in lambda of nth order. Okay, so basically it's a polynomial equation in lambda of order n if matrix is of order n. Okay, so we can write this as the polynomial equation in lambda of order n. Okay, so let this be the characteristic equation. Then this theorem says that every square matrix satisfies its own characteristic equation. Okay, so if A matrix has this as the characteristic equation, then that means the A matrix also satisfies this equation. That means we have to show that the polynomial equation, the similar equation, is satisfied by the matrix A. Okay, so that means if this is the polynomial equation, then A power n plus A1 A power n minus 1 plus A2 A power n minus 2 plus so on, an times identity must be equal to 0 matrix. Okay, so here this is a scalar 0, here is a matrix 0. Okay, of size n. Okay, now to prove this, we start with the note that in the matrix of A minus lambda I. Okay, so if you are given a matrix of A and we calculate the matrix of A minus lambda I, so what we do is we subtract lambda to the diagonal elements, okay, and non-diagonal elements remain the numbers of A, okay. So in the matrix of A minus lambda I, the elements of the matrix are of at most first degree in lambda, okay, because in the diagonal position you get a11 minus lambda, a22 minus lambda, a33 minus lambda, so those elements are of first degree in lambda, and the non-diagonal elements are just numbers, so they are of 0 degree in lambda, okay. So if you calculate the adjoint matrix, okay, so if you calculate the adjoint matrix of A minus lambda I, the elements in the adjoint matrix are polynomial of degree n minus 1 or less in lambda. This is because to calculate adjoint we remove one row and one column to calculate the cofactor at any point, okay. So the determinant of the remaining matrix will have a polynomial in lambda of degree n minus 1 or less, okay. And so the matrix of this adjoint of A minus lambda I can be written as a matrix polynomial in lambda, and this matrix we can decompose as a sum of matrices as a matrix polynomial in lambda, okay, as this, okay. So adjoint of A minus lambda I, elements are of n minus 1 or less degree in lambda, so we can have decompose it as a lambda power n minus 1 and its coefficient matrix we say it is b naught plus lambda n power n minus 2 and its coefficient matrix as b1 plus so on, plus the matrix bn minus 1 of numbers, constants. And then we know this property that A times adjoint A must be equal to determinant A into I. So this is also satisfied or true for the A minus lambda I matrix. That means A minus lambda I times adjoint of A minus lambda I must be equal to determinant of A minus lambda I times I, okay. And so by previous page we have just defined the matrix of adjoint of A minus lambda I, so we can substitute that. Determinant of A minus lambda I is given, it's a polynomial in lambda, okay. So we can substitute these two to write that A minus lambda I times the adjoint matrix of A minus lambda I must be equal to the determinant of A minus lambda I times identity, okay. And so if you compare both sides for powers of lambda, then you can equate both sides and write or you can compare the coefficients, okay. So comparing both sides for the powers of lambda, you see that on the left hand side lambda power n will be made from these product of these two terms, so coefficient is minus b naught for lambda power n, and on this side lambda power n coefficient is identity, so minus of b naught must be equal to identity. Similarly, if you calculate the coefficient of lambda power n minus 1, so that will come when this a will be multiplied to this, so a times b naught, and this second term multiplied to second term, so minus of b1, that will also give lambda power n minus 1, okay, because lambda will be multiplied here. So coefficient of lambda power n minus 1 will be a b naught minus b1, and on the right hand side it is a1 times I, okay. So this must be equal, a b naught minus b1 equal to a1I. Similarly, the coefficient of lambda power n minus 2, you will get a b1 minus b2 is equal to a2I, okay. So this, okay, and we can continue this to calculate the coefficients of lambda power n minus 3, 4 and so on. This will be the coefficient of lambda, and finally you can write the coefficient of the lambda power 0 or the coefficient of the constant. So that will be clearly a times bn minus 1, okay, equals to ani, okay, and this last one, and this is coefficient of lambda that you can check, a times the previous term bn minus 2 times minus of bn minus 1, so that's coefficient of lambda, and on the right side it will be an minus 1I, okay. So now if I multiply this first equation with a power n, multiply the second equation on both sides with a power n minus 1, the third with a power n minus 2 and so on, the last with identity, and if I add all these, So if I multiply this with a power n and this with a power n minus 1 and add, see the first term and first term will cancel out, okay, and it will be here a power n minus 1 b, and because we are multiplying here with a power n minus 2, so this term will become a power n minus 1 b 1, so these two will cancel out, okay, so these cross terms are cancelling out, okay. Second last equation is multiplied with a, so this term is a power a times bn minus 1, and here it is multiplied with the identity, so this will also cancel. So basically the left hand side will add up to 0 vector, and the right hand side it will become a power n, this is multiplied with a power n minus 1, this multiplied with a power n minus 2, this with a and this with I, so they will add up to give us the equation, okay. So pre-multiplying successively by a power n, okay, this first a power n minus 1 multiplied to this second, a power n minus 2 multiplied to third, and so on, a is multiplied to second last and identity is multiplied to last, and adding this, the left hand side will add up to 0 vector and right hand side will add up to give us the required result, okay. So this is the Cayley Hamilton theorem. This is the same polynomial equation now satisfied with the by the matrix A, okay. So this is true for any square matrix A, okay, and this result is important, we can utilize this too. So now I take two examples here. Say find the inverse of matrix by Cayley Hamilton theorem, okay. The theorem says that every square matrix satisfies its own characteristic equation. So first we need to calculate the characteristic equation of this. So if I calculate the determinant of A minus lambda I and put it equal to 0, that's the characteristic equation, okay. So that means A minus lambda I means that the diagonal elements of A are subtracted with by lambda, so this becomes 1 minus lambda and 3 minus lambda, okay, and then we can easily take the determinant, okay. Then we can solve this to write the characteristic equation, okay, which is a polynomial equation in lambda, and see is the second order matrix gives the second degree polynomial equation. So the Cayley-Hamilton theorem says that the matrix A satisfies this characteristic equation. That means A square minus 4A minus 5 must be equal to 0 matrix, okay. And we have to calculate inverse, okay. So if the matrix is invertible, so then we can pre-multiply with the inverse on both sides, okay, to write that A inverse A square will be A, minus 4 A inverse A will be I, and minus 5 A inverse into identity is minus 5 A inverse, and equal to A inverse 0 is 0, okay. So we can multiply both sides with A inverse to rewrite this as this, okay. And so we can calculate A inverse, as we can take this to other side and divide with 5. So A inverse is nothing but 1 by 5 A minus 4I, okay. And because A is known, so A minus 4I means the diagonal elements are subtracted by 4, and just multiply with 1 by 5, okay. So 1 by 5 of 1 minus 4 which is minus 3, 3 minus 4 which is minus 1, and non-diagonal remains same. So inverse of the matrix is calculated, okay, by just writing the characteristic equation and using Cayley-Hamilton theorem. The second example that I'm going to take is that to find the eigenvalues of the matrix where matrix is given this, and also find the determinant of this matrix A, okay. So now matrix is such that the diagonal elements are same and non-diagonal elements are also equal, okay, but a different scalar, okay. So if you are given a numerical of this form where the diagonal elements are of same scalar value and non-diagonal elements are of same scalar value, then we can easily use one property that if lambda is an eigenvalue of A, then lambda plus Ci is eigenvalue of A plus Ci, okay. So what we have to do is we have to subtract or add some lambda times identity such that the diagonal elements and non-diagonal element become same, okay. So if I rewrite another matrix B as A minus 6I for this example, then this will convert this matrix into the matrix of 3 3 3, okay. So because A minus 6I means that the diagonal elements are subtracted by 6, so 9 minus 6 is 3 everywhere, okay. Now clearly this B matrix is a singular matrix, okay, two rows are same, so 0 is an eigenvalue of this, okay, and clearly because all elements are same, If you row reduce it, you will get one non-zero row and all other rows will become zero. Okay, so there is only one pivot position and you have three free variables. So the null space will give three eigenvectors. Okay, so that means the eigenspace of lambda is equal to 0 for this matrix B is 3. Okay, so the matrix B is singular. Okay, lambda equal to 0 is an eigenvalue of this with algebraic multiplicity 3. Okay, because the geometric multiplicity is 3, null space is getting 3 vectors, and we know that the geometric multiplicity cannot be greater than the algebraic multiplicity. Algebraic multiplicity is always greater than equal to the geometric multiplicity. That means this lambda equal to 0 eigenvalue is repeated at least 3 times. Okay, but it cannot be 4 times because this trace of matrix is 12 here and all eigenvalues cannot be 0. Okay, so so the lambda 0 is an eigenvalue repeated 3 times. Okay, and the it's a 4 by 4 matrix. There are total 4 eigenvalues. So fourth eigenvalue is automatic, the sum of the diagonal elements. Okay, which is 12. Okay, so lambda equal to 12 is also eigenvalue of B since sum of the eigenvalues is trace of B. And so you have all the eigenvalues of B. Okay, the eigenvalues of B are 0, 0, 0 and 12. Okay, once you know the eigenvalues of B, you can calculate the eigenvalues of A by taking 6i to other sides. A is B plus 6i, so the eigenvalues of A will be lambda plus 6. Okay, so immediately you have the eigenvalues of A as 0 plus 6, 0 plus 6, 0 plus 6, 12 plus 6. Okay, so 6, 6, 6 and 18. So these are the eigenvalues of the original matrix A. Okay, and once you have the eigenvalues of A, you can find the determinant because there is another property we did in last lecture that the determinant of the matrix is equal to product of eigenvalues. So product of these four values is equal to the determinant of A. Okay, so determinant of A is 3888, which is product of the eigenvalues of A. Okay, so this is very important question. Okay, you get this kind of question in competitive exams and also in gate examination, etc. Okay, so this one is important. So that's it for today. Okay, in the next lecture we'll talk about similar matrices and diagonalization. Okay, till then have a very nice day.